Hi, welcome to this tutorial session, section 4.2, Polynomials. Polynomials. Yeah, the word polynomial, we could think of poly, meaning many, and nomial, a mathematical term, meaning, well, mathematical word, I guess, meaning term. So polynomials means many terms. The key is understanding what a single term is. What is a term? And we're going to take a look at that by doing some focus exercises from section 4.2 as well as some of the examples. And I'm actually going to start with the focus exercises first. That'll be the easiest, and I'll go to the next screen right away. This is here on page 4.2-13, focus exercise number 1. So if you want to turn there, you can know what I'm working with. Each of these is a term. Each one of these is a term. And there are different parts to the term. For example, this has a numerical part, 5, called a coefficient, something you should already be familiar with, that term. And it's got a variable part, and one of the variables apparently has an exponent. Here we've got a number part, the coefficient, variable parts, number part, variable, etc., etc., etc. And what we're going to do for each of these terms is identify the coefficient, identify what I call the variable cluster. Now the variable cluster, that phrase is something that I personally made up, and you won't find that phrase in any other book, but it makes it so much easier, I have found, to talk about terms, understanding their variable clusters, and it gives us a word and something we can refer to immediately. So anyways, it's something I made up, and I think it'll make sense when you see how it's used. In the first example, the coefficient is 5. In fact, let's do the coefficients of each one of these. Here the coefficient is -3. Here the coefficient is 5/8. Now we don't see a coefficient here, but it's important to recognize that this is being multiplied by 1, and really the coefficient there is -1. Now let me just pause for a moment and remind you that I'm expecting that you have read this section already, 4.2, or will be reading it afterwards, because there's certain things that I'm not mentioning or that I expect you to already know in my discussions of these. For our next example, the coefficient again is 1. This is a positive one this time, so we'll just say the coefficient is 1. Here the coefficient is -2, and this last one is a strange one, and I don't mean to scare you with this, but I will. No. It's 9. But it's not really a coefficient in the same sense. This is really more of a constant. And I was going to scare you with why it's a coefficient, why it's a constant. I think we'll just leave it as it is, because it'll get a little bit confusing. So I'm not here to confuse you. I'm here to help make things make more sense. So let me just leave it at that. It's a constant. We'll call it a coefficient still, but it really is a constant, kind of a dual name for the same thing. Now the variable cluster, that's the rest of the term without the coefficient. So it's, in this case, the xy to the 7th. And here, x to the 4th, y squared. So, simple. xy to the 7th. X to the 4th, y squared. Here it's just y squared. There's only one variable and it has its own power. Here it's x cubed. And here it's x to the 5th, y. So you notice that a variable cluster can contain two variables or a single variable. And believe it or not, each of these variables within the variable cluster has an exponent. Here it's clear, it's x to the 4th, y squared. Those are the exponents of the variables. We see y to the 7th. Clearly the exponent of y is 7. What about the exponent of x? Yeah, that's right. When we don't see it, oh, no, it's not 0. It's not 0. It is 1. Remember, x to the 0 is equal to the number 1, the numeral 1, the value 1. But x to the 1 is equal to x. Let me just write that up here. X to the 1 equals x. And also, x equals x to the 1. So when we see a variable without an exponent, like right here, and I put 1 in, or this y right here doesn't have an exponent. Its exponent is 1, and we can write that in whenever it's helpful to. In fact, this next one, the variable cluster, is simply w. There's no real cluster here, but the idea is it's the variable part of the term, and what's its exponent? That's right, it's 1. And I can put that 1 in if it's helpful, and I'll put it in here too. Why not? This last term, as we see it, has no variable cluster. So I'll just write that in real quickly here, or you could write none, that'd be okay. Now the degree of the term, hopefully you've done the reading already, but I'll just mention briefly, the degree of a term is the number of variable factors in the term. The number of variable factors in the term. What that means is, for example, take x cubed right here. That's x times x times x. That has 3 variable factors, so the degree is 3. This y squared is y times y, so its degree is 2 variable factors. Look at x to the 4th and y squared. There are 4 variable factors here and 2 more variable factors with the y. Now we can't combine that to a single x to a power or y to a power because they have different bases. But still, if we were to multiply this all out, we'd see x times x times x times x times y, and a total of 6 variable factors. So it's a matter simply of saying 4 plus 2 is 6. We have 6 variable factors. The degree is 6. Now, if you don't quite get that, you don't quite understand it, believe it and work with it. It's okay. Maybe you can ask some questions about it. This first one I didn't even do yet. Remember, the x has a power of 1, so its degree is 8. Its degree is 8. We have to consider that 1 that's there. Likewise, down here, the degree is 6. We have 5 x variable factors and 1 y factor, so a total of 6 factors. This has a degree of 1. This has a degree of 1. And when there's no variable cluster, the degree is 0. So the degree of a constant is just 0. Okay? Well, that's focus exercise 1 from page 13 in section 4.2. Let's move on to section 4.28. My screen just went dark, so I'm going to try this again. Excuse me. Much better. I imagine you could have seen it both times, but mine didn't work out so well. When we identify terms in a polynomial, we can count them real quickly. For example, this one has 2 terms. And the special name, I'm not going to do an example here beyond this, but the special name for this is a binomial. Bi meaning 2. Excuse me. It's a binomial. When there are 3 terms, as we see in the second example, that's a trinomial. And if it has more than 3, we don't have a special name for it. It's just called a polynomial. So polynomial, these are all polynomials. Even these are polynomials up here, but they have special names. Oh, by the way, if it has just 1 term, we call that a monomial. Mono meaning 1. Okay, we don't have any monomials listed here, though the individual terms, that's a monomial, but together, because they're being subtracted or added, that makes them, binomial or trinomial, polynomial, etc., etc. Descending order means highest degreed term is written first. Now remember, the degree has only to do with the exponent, with the number of variable factors. So when I see this has the highest degree, so that's going to be written first. And that term, we cannot ignore the fact that there's a minus sign in front of it. That is a negative 7x cubed. So I'm going to write that as a negative 7x cubed. The first term is a positive 4x, but if we switch these terms around like we're doing, that 4x has to come on the other side and is represented by plus 4x. That makes it, it indicates that it's a positive 4x. Let's see, what about this next one? X squared is the highest degreed power, then the 6x, so plus 6x, and then the minus 3. Constants will always be last. Here we have negative 2x cubed. Notice that I called it a negative 2x cubed because of that minus sign in front. And it looks like we have a negative 8x squared, a positive 5x, and a positive 1. Putting them in descending, which means, it gets lower and lower and lower, and you can see the degrees do get lower and lower and lower with each term. Not the coefficients. They have nothing to do with the descending order, with the degree, just the exponent. Negative x cubed plus 2x squared minus 4x plus 9. And lastly, let's see, looks like we have a negative x to the 6th as our highest power, so that becomes the first term, and then minus 3x to the 4th plus 9x squared and minus 2x. So that one didn't have a constant that we can see, and so it didn't end in a constant. I guess you could say it's plus 0 at the end, but we certainly don't need to write that. Now, the leading coefficient is always the first term after it's been put in descending order. So the leading coefficient is going to be that first term's coefficient. So what do we see here for the very first term in its coefficient? Negative 7. Looking at the first term, its coefficient is, that's right, 1. Here the first term's coefficient is negative 2. And here the first term, we don't see, I could put a 1 there if I needed to, but its coefficient is negative 1. And the same is true for here. The coefficient on the first term, it's called the lead coefficient or leading coefficient, is also negative 1. The degree of the polynomial is the degree of the first term. So I'm going to say here equals degree of, I'm going to call it this way, lead term or leading term. The degree of the polynomial, it's not all of the powers. In other words, we don't come down here and say, oh, well, this one has a power of 3 and a power of 2 and a power of 1, that we should add all of those together. No, we shouldn't. And the reason we don't need to add them together is because, remember, degree has to do with the number of variable factors. Factors means multiplication. So if I took this second example right here and I wrote it out, it would be something like this. X times x plus 6 times x and then minus 3. And notice here that the x's here there are two variable factors. But because we have a plus sign now, that this variable here is not associated with those because of the plus sign. So since factors means multiplication, and we have this addition sign in between, these are kept separate. So all we can see here are two variable factors as the highest, as the most. And so that is the degree of this polynomial. It has a degree of 2. We call it a second degree polynomial. I'll just write it here as a degree of 2. Back to the first one, it has a degree of 3. The leading term degree is 3, so the degree of the whole polynomial is 3. And again, we can't decide on the leading term until after we put it in descending order. So don't make that decision here. Write it in descending order and then decide what the leading term is. We can find the lead coefficient and the degree of the polynomial from that single term. Here the degree also is 3. So let me write that in. The degree of the next one, well, 3. I'm not very creative, it looks like. 3. Oh, here's one. The degree on this one is 6. Again, it's just the degree of the lead term. There's probably more explanation in the book about that. Okay, next example. Combining like terms. Combining like terms. This is page 4.2-6, example 9. Let me turn to that page. Here it is. And we can combine like terms by combining the coefficients as long as the variable clusters are the same. Remember how I said that word variable clusters? I made that up, but it's so useful because now I can use it in this definition that the variable clusters are exactly the same. That's when we have like terms. The variable clusters are exactly the same. So, part A is 8x cubed y squared plus 2x cubed y squared. Notice those variable clusters are exactly the same. Same variables with their same coefficients, and this is simply 8 plus 2 is 10 x cubed y squared. And go ahead and read, the explanation for this if that would be helpful. Well, I want you to read it. Of course it's going to be helpful. Negative 4x cubed plus 9x cubed is negative 4 plus 9 is positive 5. You might even want to put that little plus sign for emphasis, not necessary. X cubed. And notice that the variable cluster here, where there's 8 of these plus 2 of these equals 10 of these, this answer, this variable cluster, is exactly the same variable cluster here and here. And whenever they're like terms, that will be true, so that all that really combines are the coefficients. Negative 4 and 9 is positive 5. C, 10y squared minus 6y squared. 10 minus 6 is 4, also y squared. Letter D says we have negative 8x plus x. Now, here, we don't see the coefficient of that second term, so I'm going to put it in and help us recognize that that's negative 8 plus 1, which is negative 7, and the same term, x. Let's see. E, negative 3x to the fourth minus 2x to the fourth. It's negative 5x to the fourth. F, here's one that's important to note. It says 4x squared plus 3x equals 4x squared plus 3x. Notice these did not combine. And the reason is because the variable cluster is different. This is x squared, this first one, and this is 3x. So different variable clusters, meaning different terms, not like terms. They cannot be combined. And sometimes I'll just go ahead and skip to letter H. Well, I'm just skipping G. Big deal, huh? Here's letter H. Says we have 7x minus 6x plus 3y minus 5y. And what we can do is combine the first two because they're like terms, and then separately combine the last two because they're like terms. And we'll get 1x, or x, minus 2y. Now, as I pointed out, I called that 1x minus 2y. And it's because we have, first of all, 7 minus 6 is 1. But technically, well, I shouldn't say technically, but typically we don't write the 1 in. We usually leave it off. It's sometimes helpful to include it when it's not there, but if we don't need it, oftentimes it's left off. Just like that exponent there is 1, and we don't write it as a 1. We usually leave it off as well. And then 3 minus 5 is negative 2, and that shows up as a minus 2y. So that's how the negative shows up, negative 2y. Okay? Next example. I want to remind you also that, if there's any time when you need to rewind this, you can simply use the scroll bar, use your mouse on the scroll bar to pull it back to an earlier part, or skip ahead if you wish. Here's example 5 on page 4.2-7. I'm not going to do many of these. I will do just a couple. Here's 5a, which says we have 5 times 2x cubed plus 3x. And we're going to distribute that 5 to each of them. And as we do, the 5 multiplies only by the coefficient. The variable cluster part of it is unaffected. So here we get 5 times 2 is 10x cubed plus 5 times 3 is 15x. Let me skip ahead to letter C, and it says we have a negative 2 times 3x plus 1. Again, we're going to distribute not 2, but negative 2. And we have to multiply negative 2 times positive 3, which is a negative 6x. And negative 2 times positive 1 is a negative 2, or minus 2. Letter E is very simple. It asks us to distribute 1 to the quantity 6x cubed plus x minus 4. And multiplying by 1 couldn't be simpler. It's just 1 times each of these. And so we just get the 6x cubed plus x minus 4. Multiplying by negative 1, however, as we see in, let's skip all the way up to letter I, exercise I. Oh, you know what? No, I'm going to do letter F first. See if I can turn that into an F, which is negative 1 times negative 3x squared plus 2x minus 5. We're going to distribute all of negative 1 to each of these. And what we'll get is negative 1 times negative 3 is positive 3x squared. Negative 1 times 2x is a negative. So negative 1 times negative times positive. Negative 2x. Negative 1 times negative 5 is positive 5, or plus 5. That's how that shows up. Notice that the effect, really, when multiplying by negative 1, is to change all of the signs. And, multiplying by 1 doesn't change anything, but multiplying by negative 1 changes only the sign. So negative 3x squared here, positive 3x squared. Positive 2x, negative 2x. Negative 5, positive 5. Took the opposite of everything, didn't it? And that's actually what letter I does. It says the negative of means the opposite of negative x squared plus 6x minus 1. Now, you can just say the opposite of and take the opposite of everything, or, as we've seen before, we can always put a 1 there. And now we're going to distribute, I'll use a different color here, distribute negative 1 to each of those. Multiplying each by negative 1 makes this become a positive. And I'll put a plus sign there for emphasis. A positive x squared, a minus 6x, or negative 6x, and a positive 1. All right? So that's the distributive property quickly on page 4.2-7, exercise 5. Let's go on to our next. Looks like we're on example 10 now, on page 8. And this is adding polynomials. And I'll just do part A on this one. And it says that we have 3x minus 5 plus x squared plus 2 plus 8x minus 4x squared. And notice that I have these in parentheses. Well, the best way to eliminate parentheses is to distribute whatever number's in front of them. And yet we don't see a number. That's when we put 1. And we put 1. We put 1 in front of each of them. If not written, we put it in mentally. And we distribute 1. And as I mentioned, distributing 1 is the easiest trick of all. And we simply get 3x minus 5 plus x squared. Multiplying by 1 changes nothing. And this also here is a positive 1. So when we distribute that positive 1, it's just we just get exactly what we get. 1 times 2 is 2. 1 times 8x is 8x. 1 times negative 4x squared is still negative 4x squared. When it's positive 1, it doesn't change anything. Not the numbers, not the signs, not the variables. Multiplying by 1 is terrific. However, now we've got a little bit, not a mess, but we've got a lot of terms here. And the problem also says Oh, it doesn't. But you know what? We're going to put this in descending order. That means the highest terms first. And we have a positive x squared and a negative 4x squared. So let me write that out. Actually, I'll keep it in that color. We have x squared and a negative 4x squared. And let's see, the extras, we have a 3x and an 8x. That's a positive 3x and a positive 8x. And those are the x terms. And lastly will be the constants. And we have a negative 5 and a positive 2, or a minus 5 and a plus 2. And finally, when we combine them all together, keep in mind that this is a 1x squared. 1 minus 4 is negative 3x squared. 3 plus 8 is 11, so that's a positive 11x. Negative 5 plus 2 is a negative 3. And that's how we add polynomials. Simply put a 1 in front of each parenthesis and distribute. Couldn't be simpler. Combining like terms and putting them in the right order could be a little bit of a challenge, but it's not much. Lastly, we have example 11 on page 10, and I will also do part A. It says that we have this quantity, 3x minus 5 plus x squared, minus this time 2 plus 8x minus 4x squared. And as I did before with the addition, I'm going to put a 1 in front of each. But the major difference here is this. Distributing 1, not a problem. That works exactly the same. Here, though, we need to treat this as a negative 1. Might even be helpful to circle it like I did. And distribute a negative 1 to each of those. And that will change their signs. But let's not rush through, just one step at a time. 1 times 3x is 3x, 1 times negative 5 is negative 5, and 1 times x squared is just x squared. But negative 1 times 2 is a negative 2. Negative 1 times 8x is a negative 8x. Negative 1 times negative 4x squared is a positive 4x squared. And again, combining like terms and putting them in descending order, here we have x squared plus 4x squared, and 3x and a negative 8x, so it's a positive 3x minus 8x. I'm doing this step here to reorganize them to help get things together and make it easier to work with. Minus 5, it's a negative 5 and a negative 2. Minus 5 minus 2. And now when we complete this, remember I have a 1x squared here. That's a total of 5x squared. Minus 5x minus 7. And that's the answer. Let me double check. Oh yeah, got it right. Good. That's how to work with polynomials. So please learn this well, read the material, and if you have any questions, please send an email or put a message on the discussion board. All right? Thank you. Wait for the next one.